What's up, everyone? Yeah, fine. So let's start. Earlier we saw these simulations with the GCM. It does a pretty good job when you're looking at the seasonal cycle. But you can't understand why it is doing a good job. And we want to know things. We want to know why certain things happen. We want insight. And the only way out is to simplify the equations. We don't have any other way forward. So one major simplification we're going to make is in the vertical. We're going to assume that the ocean is just consisting of two layers and it has a flat bottom. So you have a mixed layer kind of upper layer of density rho1, which is less than the density rho2 of the lower layer. So the technoplane is now just an interface between the two layers. We also don't allow any mixing between the two layers. This is a dynamical reduced gravity model. Now it's called a reduced gravity model because in this model, G gets multiplied by rho2 minus rho1 by rho bar, where rho bar is an average density. Practically, for all practical purposes, we can consider it to be 1. Rho2 minus rho1 is small, and there are two things that happen. One is that eta, the displacement of the surface of the sea, is much smaller than the displacement of the interface. A rule of thumb would be that if eta changes by something like 10 centimeters, the change in the interface will be on the order of 30 meters. The other change that takes place is in the speed of the wave. If you were to look at the propagations, the gravity wave speed, if you had just the uniform density, is square root of g into h. What you get now is an interfacial wave, that is, this interface will move at the speed given by square root of g prime into h, where g prime is that reduced gravity, delta rho by rho into g. If you have a 4 kilometer deep ocean, that's 4,000 meters, g is roughly 10, so your wave speed, which determines the movement of the surface in the case of tides, would be of the order of 2 meters per second, 200 centimeters per second, square root of 40,000. Now you have delta rho by rho, and the kind of speeds you get is of the order of 2 meters per second. So it's much more slowly moving, and therefore you can track it with instruments like the altimeter or tide gauges. It's called a 1.5 layer model because the only active layer is the upper layer. The moment you assume this layer to be infinitely deep, or this edge, the height of this layer is much greater than the height of this one, it turns out that to balance mass, this layer practically drops out. So the currents here are vanishingly small. So this kind of a model cannot simulate an undercurrent. It has its limitations, but it turns out to be very useful if you are trying to understand why some of those currents behave the way they do. This is a simulation with a nonlinear version. The equation terms are not dropped of this reduced gravity model. The color is sea level and the vectors are currents. I'll show you an animation later. Basically, you see these features. You have a high sea level here in January, it moves offshore. You have a gyre in March, the current is stronger in March than it is in July, and the West Coast current in winter flows into the wind. So it does roughly what the GCM does, except that now you have a single layer, so you don't get the undercurrent and other features. It also produces the Divecha, the Somali current, or most of observations that you see in the mountain ocean. The trouble is that, in spite of the major simplification we have made in the vertical, it's still too complicated for us to understand and answer the questions that we had asked. And right now we are interested in just 2 or 3 things. What is the West Indian coastal current flowing to the wind in January? Why is the East India coastal current weaker in July as compared to March, April? You can see that in the circulation and in the GCM. And why is the filling weaker of the East Coast, where the winds are practically along the coast in July, as compared to the West Coast, where the onshore winds are much weaker? And you can see that sea level drop here is less. You see yellow colors, while here it is green. The sea level has decreased, is lower of the West Coast, which means the thermocline has come up more. So the observations are pretty well simulated. And the major simplification we are going to make is that we linearize the model. So what do we mean by linear? What's a nonlinear system? In a nonlinear system, output is not proportional to the input. If I have inputs I1 and I2 and outputs O1 and O2, O2 plus O1 is not proportional to I2 plus I1. That's the essential feature of nonlinearity. The whole is therefore not equal to the sum of the parts. So if I break my system into multiple pieces, I can't just add them and expect to get the sum total. In simple terms, we cannot break the forcing, that is the wind, into pieces. That is the drawback in a nonlinear system. And that essentially comes from the Q dot grad U term in the momentum equations. In a linear system, on the other hand, output is proportional to input. So if I have O1 and I1 and O2 and I2, O2 plus O1 is proportional to I2 plus I1. That's the characteristic of a straight line. The whole is equal to the sum of the parts. Can rupture forcing into pieces? So principle of superposition, which we have used in school, is valid. Before we start doing anything with the forcing, we still have to show one thing, that the linear system is a reasonable measure of what is observed. If the linearization does not lead to a simulation that is reasonable, then there's no purpose in breaking the forcing into pieces. You can carry out an analysis, but it will explain nothing, because the total, the whole, is not commensurate with what you see in the observations. That's the next step, the linear simulation. The equations have been linearized here. The momentum equations no longer have the nonlinear terms. And you get practically the same kind of behavior with 2 differences. One is that in a linear system, the wave speed is square root of g prime h bar. This is something that happens the moment you linearize the equations. In a nonlinear system, it is square root of g prime h, where h is the instantaneous thickness. So basically, there's going to be small departures from the mean, and h bar, that is the average thickness of the upper layer, is now what determines the wave speed. So in reality, the low sea level features will move more slowly because they have thinner upper layer in comparison to the high sea level features. But in the linear system, they're going to move at the same speed because it's square root of g prime h bar. That is one change. So the timings tend to go a bit off, but not by too much. It's still good enough for you to use it. The other change that takes place is over here. Of Somalia, in July and September, you see 2 gyres. There are 2 highs in sea level. One to the south is called the Great One, the one to the north is called the Socotra idea. In the linear system, they coalesce into a single high. Apart from this one major difference, the linear system is practically the same as the nonlinear one. This is a major success. There's no way with the linear model to explain this one, why you have 2 eddies. But if we are willing to forego that part, the rest of it is there. So now we can experiment with the linear model. So this is a set of experiments that were carried out with this model. On the left-hand side, you have an experiment in which the winds exist only along the east coast of India, forcing only by east coast winds. This is the panels on the right hand side. Now this is done in a different fashion because one way to carry out these experiments is to manipulate the winds. That is, you put the winds only along the coast of India, east coast of India, and drop the winds elsewhere. The moment you do that, however, you have to taper off the winds to zero. And when you do that, you introduce the spurious wind curve. So there is no way to tamper with the forcing without creating another disturbance. You create a response because you are manipulating the forcing field, and you know that the curve of wind is going to create a special kind of circulation. There is no way to ignore it. So this is not being done in that fashion. The model has got only one active layer, and it's so simple that the way it's being done here is to tamper with the boundary condition. What has been done in this case is to say that when I'm looking at the east coast winds, what causes the changes along the east coast? It is the Alongshore wind creating equal flow into or out of the boundary. If I tamper that boundary condition, allow the flow to go through the boundary, then there will be no response to the local wind. And in a linear system, the sum of the parts is equal to the whole. So I take the linear response, the full linear response, subtract out from that the solution in which I have tampered with the boundary condition to allow the equal flow to go in and out of the boundary. Now the response that I get, the difference of these two simulations, is just the forcing by the east coast winds. I can do the same thing with the west coast winds. So this set of panels on the left is forcing just by west coast winds. Now look at what happens when you have forcing with just east coast winds. You would expect a strong current when the wind is strong, and that's what you get. In July the current is strong, and in March it gets weak. But the response is not localized to the east coast of India. The bigger response that you see is of the west coast of India, in the eastern Arabian Sea, and we can propagate to the interior of the basin, having an impact as far off as Somalia. So you have winds blowing out here along the east coast of India. So you have winds, and these winds change in time. They create an equal flow that goes into or out of the boundary. When it goes into the coast, there's downwind. When it goes away from the coast, there's upwind. There's equal flow. But this equal flow is changing in time. I mean, if you have a simple harmonic, a sine wave, the response has to be a sine in a linear system. All that you are doing is oscillating out here. But this oscillation cannot really be confined to that region where it's generated. Because you have waves that can propagate along the bottom. And that is what brings the response from the east coast to the west coast. And then it goes off westward into the rest of the Arabian Sea. These waves that propagate along the boundary are called coastal Kelvin waves, named after Lord Kelvin, with his concept. And the waves that propagate away from the boundary, due west, are called Rossby waves. Yes.
Is there any contribution from the point of view to integration?
Is there any contribution from the point
Variability oscillation in integration?
Not looking at variability oscillation. Okay? Variability oscillation is a feature that has a time scale much less than that of the season. Not even looking at it. I'm looking only at what can be described by monthly data. We have one value per month. We have averaged out the data to get one value per month. Only those kind of features we are looking at right now. We can't be HO and other things in the question session maybe the last half hour. So this wave that goes offshore, away from the west coast of India, westward into the Arabian Sea, is called a Rossby wave. When you look at what happened with just the west coast winds, now they are much weaker, offshore winds. As you would expect, the response is much weaker. It turns out that if I want to explain the seasonal cycle of sea level and current of the west coast of India, say, oh, I have a tide gauge of I want to explain why the sea level behaves the way it does. or I have a current meter moving and I want to explain the signal cycle of that current. Why does the resting opposite current flow into the wind in general? The reason is that the forcing comes from the east coast. It is the east coast wind that is oscillating in time. And driving a Kelvin wave that runs around Sri Lanka to propagate forward along the west coast of India. These Kelvin waves propagate with the coast only right in the northern hemisphere. So they were to go from the northern plain towards Sri Lanka and then forward along the west coast of India. So this pressure gradient that you need in this case is set up by the Kelvin wave. When you have a downwelling Kelvin wave as you see out here coming down south, it raises the sea level at the southern tip of India. Sea level is lower, north along the west coast. That sea level drives the current, because you have dE by dt is equal to minus v by dy, and y is the Alongshore coordinate. So that is the balance that sets it, and you have a wave that goes north along the west coast of India. So if you look at the cyclical cycle along the west coast, it's driven more from the east coast of India than by the local west coast winds, because the longshore winds are much weaker along the west coast. Let's leave out this solution for the time being. If you were to get rid of all the longshore winds, it doesn't mean the forcing is gone as far as the coast is concerned, because you have wind curl in the open ocean, and the wind curl is going to create oscillations. In the spherical solution, you have a Rossby wave, but the spherical solution is steady state solution, which means it's the t tending to infinity limit of the Laplace transform. That is the way you look at it. So what is happening in this case is that you have a time-dependent spherical solution. So you're going to create the same kind of charges, but they're going to propagate westward in time. If you take t tending to infinity, if you could do that, this is not steady state, but if you did that, you would get a steady response. And that is exactly what the spherical solution is. You take the Laplace transform, take the t tending to infinity limit, the steady limit, and you get those steady charges. It is the other processes, that is the wind curl over the open ocean and forcing from the equator, the winds blowing over the equatorial ocean, that drive the bulk of the extreme atmosphere. Let's show a response coming from local winds, because they show you a seasonal cycle. But that can't explain why the current is strong in March. The current is strong in March because of the curl of winds over the open bay. So you have these Rossby waves that are triggered over the open bay. You basically have a curl of winds. We saw that if you have an anticyclonic curl, it will raise the sea level. But there is a d by dt term. It can't remain isolated. It can't remain stationary over there. It propagates westward, because that is the only solution that the system of equations will allow. It propagates westward, and over time it will reach the eastern boundary. And when it reaches the eastern boundary, you can't have flow into the boundary. You have to cancel the flow into the boundary, and the way you do it is by reflecting the thing. The moment you reflect the thing, you get the boundary current. So what you are seeing in March out here is the strong east coastal current that arises as a consequence of these waves radiating westward across the Mediterranean. And it is this forcing driven by processes that are remote when compared with the location that we are looking at. Say I have a parameter or some measuring instrument stationed on Goa. I am making my measurements out there, but my physics doesn't allow me to look only at a small region around Goa. The trouble is that the basin is interconnected. At the equator, you have two waves, equatorial Rossby wave and equatorial Kelvin wave. The equatorial Kelvin wave propagates eastward along the equator. The equatorial Rossby wave propagates westward along the equator. Both are parallel. Because just like a coast, the equator is a dynamical boundary. Because F changes sign across it. So it acts like a boundary. And in the linear system, except that a boundary like the western boundary, it's very difficult to get water to cross the equator. Very difficult to do it. It's only at western boundary where you can push water from one hemisphere to the other. So at the equator, you will rarely see any such thing happening. So you have equatorial Rossby waves, equatorial Kelvin waves, and then you have coastal Kelvin waves. And when I say equatorial Rossby waves, they are not as trapped as the equatorial Kelvin waves. The equatorial calibrate has an E-folding scale, that is the decay away from the equator in this case, of the order of 2 to 3 degrees. The equatorial Rossby rate, because of the kind of functions that you get, is it's called harmonic function. It's related to the parabolic cylinder functions. You get oscillations that decay as you go away from the equator. But you can see many figures. You can simplify the model even further. And if you look at the southern tip of Sri Lanka, you imagine that this is the Bay of Bengal, this is the Arabian Sea, and India is just behind it. So you have the southern tip of Sri Lanka, right? And you have a current there that oscillates in time. In summer, that current flows eastward, and in winter, the current flows westward. These are measurements using acoustic Doppler current profilers moved south of Sri Lanka, reported in short April 1994. This is the transport associated with monsoon current, summer monsoon current, and winter monsoon current. So if I want to create a very simple model of the West India coastal current, the simplest one I can get is one in which I consider the west coast of India now limited 6 degrees north of the equator. It exists only from 6 degrees northwards as a vertical model, meridional boundary. That's the simplest possible approximation I can make. And I throw in oscillating current. This is a oscillating function that oscillates in time. So it flows eastward one half of the cycle and it flows westward the other half of the cycle. It's a pure sinusoid. Just mimicking this, but simplified. The question is, I have nothing else. I have only harmonic functions. It's an innocent model. On the equatorial data plane, you get functions that are called harmonic functions. And there are only 2 kinds of waves that are possible. The equatorial Rossby waves and the equatorial Kelvin waves. But the equatorial Kelvin wave is out. Because I have no forcing that goes within 3 degrees of the equator. This current is only there before now. So the only wave I can expect now is the equatorial Rossby. There's nothing else in my system. I've thrown out everything else. I can't create a simpler model. So all I'm doing is describing that current. It's an east-west current oscillating in time at the southern tip of this variable boundary. The question is, will it reproduce what we see in the observations? The answer is yes, it does that. So this is one half of the cycle of a 360-day period. You see the highs moving offshore. I'll show you an animation a little later. This is amazing. There's nothing out here. There's been an error of the calculation. So this is a paper pen solution. It's just that the number of terms was very high. I think it was around 1,000 or so terms in Y. Because I told you this Rossby wave has many variables. Each of those expressions that you get is a mode. And we have to add something like 1,000 modes to get this solution. And in spite of that, there's an error. So why is there no flow across the coast? It is because that is the boundary condition. We have to satisfy that condition to some level of accuracy. So that cross-shore flow in this case, you had to go to 0. So as many modes as were required to satisfy the condition had to be added. Once that is done, the rest of the solution shows up. I can now play with this model. I change the period to 60 days. Out here. Now you can see that the current is trapped forward of about 10 north. It is supposed to be there is nothing radiating off. But if you look carefully, you see south of 10 north, there are alternating times of highs and lows. But now they are more compressed. So you can see, if you look at the altimeter data, you will see small deceleration, small jumps in the literature throughout. Everybody calls them eddies, without exception. It's not necessary that there is. Eddy, by definition in fluid dynamics, is a nonlinear phenomenon. These are not eddies. This is a totally linear system. No eddies can exist. These are small decelerations, and they are possible. And if you look at these high and low in the altimeter data, you find this large scale signal a broad term, and embedded within that are these smaller features. Are they linear? I'm not sure. Are they non-linear? I'm not sure. Nobody has studied them. They just dismissed as is, but they need not be this. Cut down the linear coordinates, the entire separation is trapped. And this result of trapping at the coast, forward of what is called a critical latitude, was the subject of one of the most remarkable theses, PhD thesis in oceanography. Never published. It was by Dennis Moore in 1968. It's available only in scanned form from Harvard. So Moore never published it. So even now, if you have to cite that work, and you have no choice but to cite it if you are looking at interannual oceanography, it is in the form of PhD thesis. Remarkable piece of work. What he showed us why you have a critical latitude, forward of which you can show that what you are getting is actually a coastal Kelvin, and the equator of which you will get the westward propagating Rossby wave. Here the wavelength of the Rossby wave is small, and that is why the offshore length scale is small. The wavelength is much larger at higher periods, and therefore its gyres that you see have a more elongated extent. But this is the simplest possible model that you can get for the West India coastal current. So, what are these large-scale planetary waves? This is a rectangular basin. It is an analytic solution from Julian McCreary's paper, 1976. What we have is a forcing, wind forcing, in just this patch. This is the equator, and this is about 2,000 kilometers away from the equator. So there's a wind forcing that is restricted to a patch out here. It doesn't extend to these boundaries. It doesn't extend to the western and eastern boundaries. It just switches on the wind and sees what happens. When you switch on the winds, you get a Kelvin wave that propagates the wave from the boundary of the forcing towards the east. And you get the Rossby wave that propagates the other way. At the equator, the Rossby wave speed is 1/3 that of the Kelvin wave. So you see the Kelvin wave moving away faster. But once it hits this boundary, the current associated with the wave has to be cancelled at the boundary. You cannot have flow into the boundary. You cannot have water flowing through this. Okay. The current has to go to zero. The normal flow. The moment you cancel that, you get a reflected Rossby wave. That's what you see coming back in. And the reflected Rossby wave has a length scale, a meridional length scale, a north-south length scale that is much larger. And you will see this energy going forward and again radiating offshore. So if I have forcing just at the equator, south of Sri Lanka, I can produce a circulation in the Bay of Bengal. This is called remote forcing. You have a forcing in some region and you have an effect somewhere else. This is ubiquitous in the ocean. You have a storm blowing in the South Indian Ocean, you will have swells of Goa. It makes a difference. If you're going out on a cruise and making measurements, it's not enough to know what are the local conditions. You have swells that can become very difficult to deploy in this region. My colleagues are on a ship right now, they're facing that problem. Some things don't work when the swells are large. It's a storm that occurred maybe a few days back, somewhere else, and those swells have propagated into the Arabian Sea and are causing trouble. Somebody who just wants to make some measurements. Likewise, these waves, they also propagate away from where the wind generates. And after some time, maybe a few months, they affect the circulation at some other place. So what are the kind of waves that we get on this equatorial equator? There's the equatorial Kelvin, it propagates eastward around the equator. Speed is 2 meters per second, roughly, depending on certification. It's trapped within about 3 degrees of the equator. The equatorial Rossby wave propagates westward around the equator. Speed at the equator is 1/3 that of the equatorial Kelvin wave. Its speed is proportional to 1 by y squared, where y is the distance from the equator along a meridian. So if you come to the equator, the Rossby wave would have a speed of something like 60 centimeters per second. But if you come to Cochin, which is 10 knots roughly, you find that the Rossby space speed is already 3 meters per second. So it's a very slow moving wave. It's going to take a long time to cross the basin. And if you go to 30 knots, 1/10 of that, 1 centimeter per second. At 1 centimeter per second, you can have a Rossby wave. Imagine the time it's going to take to cross the entire Pacific. But today, the altimeters have been kept. There's a remarkable paper in Nature by Jacobs et al. In 1982, El Nino created an equatorial calendar. The equatorial calendar is the eastern boundary of the Pacific. It propagated eastward along the equatorial Pacific, hit the eastern boundary of Peru, reflected as well as the energy went forward along the coast of Chile down south and along the coast of the United States. That was practically instantaneous as far as the timescales of the Rossby wave are concerned. But off San Francisco or Los Angeles, 30 north, the Rossby wave is now going westward at 1 centimeter per second. 10 years later, in 1992, Jacobs et al. Could see the effect of the 1982 El Nino in the Kuroshio extension of Japan. The western boundary current of Japan, it has an extension called the Kuroshio extension. That was being affected by a phenomenon that had occurred in the equatorial Pacific 10 years earlier. So these waves can have long-lasting effects. That is the reason we study them. So when you're looking at those sea level curves, they're not just about fitting a straight line. There's a lot that has to be understood in the regs. And if you don't understand them, there's no way to make sense in a straight line, because a straight line is fitted over a limited record. That's something you cannot do. The coastal calendar is the third way of doing this. It's coastally tracked, it propagates along the coast, it goes to the right in the northern hemisphere. Speed is same as that of the equatorial, it's determined by stratification. And the radius mostly is when propagating outward along the eastern boundary. And that's what we saw. When the calendar goes outward along the west coast of India, it's an eastern boundary, energy radius offshore as Rossby wave. There's also a wave called the Anai wave, but that's of interest only at intraseasonal periods. So we're going to ignore that here. So this is the summary in one picture. You can call it a leaky wave guide. This is the equatorial wave guide determined by the Kelvin wave, the blue one, tracked within about 3 degrees of the equator. So if you trigger a Kelvin wave anywhere out here, let's say, the west of the Indian Ocean, it will propagate along the equator towards the east. But once it hits the eastern boundary, by Moore's reflection rules, it will generate a westward propagating Rossby wave. And the reflection of the equatorial Kelvin wave cannot be handled with one meridional mode of the westward propagating Rossby wave. You need an infinity of modes to cancel that cross-shore current. That is what sets up this forward propagation of energy. Because you have a lot of those wiggles. And once you have those wiggles, you find energy going forward. So you have a coastal wave guide. You also have winds that blow along the coast, generating coastal Kelvin waves. So you can generate energy along the coast, propagating with the coast to the right and the northern hemisphere. The coastal Kelvin wave south of Sri Lanka has a refolding scale. They decay offshore of about 2 degrees. The southern tip of Sri Lanka lies at 6 knots. So the separation between them is about a degree. The equatorial wave guide and the coastal wave guide south of Sri Lanka are separated. Just another accident of geography. That is what allows the Kelvin wave generator of the east coast of India to go into the Arabian Sea and have an impact on the West India coastal current. That's why the seasonal cycle of what we see of Goa is determined more by what happens, the kind of winds that blow along the east coast of India. It is because of this separation. If this was not the case, then this Kelvin wave would get enmeshed with the equatorial system, and you wouldn't have as clear an effect out here. But the moment you have a Kelvin wave propagating forward along the eastern boundary, that is the eastern boundary of the Bay or the Arabian Sea, you have Rossby waves radiating offshore. They radiate offshore much faster as you go closer to the equator. It's 1 by y squared, that's proportionality. You can also generate Rossby waves in the interior of the basin. When they hit the western boundary, after propagating westward across the basin, you have to reflect that cross-shore current. You have to cancel it. So you have to generate a reflected wave. The moment you do that, we generate a coastal Kelvin wave. So you have a wave guide in the equator, you have a wave guide in the coast, you have processes taking place in the interior of the basin, and they all related. So even if I want to study what happens on Goa, I don't have a choice. I have to model the entire Indian Ocean. This is the indication. The existence of this leaky wave guide, once the latency of the wave will go in the Indian Ocean, is a single dynamic entity. I cannot break them. which must be monitored as a whole able to simulate the seasonal circulation in spots. So if I want to explain the seasonal cycle of sea level or current or both, I need to model the entire basin. So the summary for the Indian Ocean, the North Indian Ocean is different. It is small. It has time-dependent wind force. It has a seasonal reversing circulation, and the mean circulation is much weaker than the seasonal cycle, because the mean winds are much weaker than the seasonal cycle of the winds. The steady state ranges, where storm and monk are no longer valid. You cannot ignore time dependence. You cannot drop the tendency time. You cannot drop the d by dt time. It's a tropical basin, which implies that large-scale planetary waves propagate faster across the basin. 1 by y square, that's the speed of the Rossby wave proportionality. Most of you observe seasonal cycle in the Pacific Atlantic of surface circulation as explained by linear wave theory. Remote forcing is important. Even if I want to understand just what happens or go on, I need to understand what is happening over the entire basin. I cannot ignore it. It has been a long time. Modern oceanography of the North Indian Ocean starts with the International Indian Ocean Expedition in the 1960s. The Challenger expedition ignored this basin. It was provincial. We're looking at the global oceans, Atlantic, Pacific, the Antarctic circumpolar current, and they just cut across the Indian Ocean from the Cape of Good Hope through the seas of Indonesia into the Pacific. North Indian Ocean was ignored. But it's a remarkable place. It's the only part where western boundary current, like the Somali current, reverses with season. So what kind of circulation do you see? What kind of dynamics will exist? This is what excited oceanographers all over the world, leading to the International Indian Ocean Expedition in the 1960s. And the institute I come from is a consequence of that. When Goa was liberated in 1961, around the time the IISc was being planned, and Pandit Nehru decided that it's a good place to set up an institute of oceanography. So that's why I came. Basic theory is contained in 3 papers or theses. The first is Taro Matsuno, 1966, flood waves and equatorial beta wave. These are the dispersion curves for waves. Next one was the PhD thesis, there is no. We showed how the reflected equatorial waves at the eastern ocean boundary. It's much easier to do it at the western boundary. It was the eastern boundary problem that was very hard, and it was Dennis Moore's great contribution. The next one was James Light in 1969, faster propagation at the equator. He realized that it has a major implication. Unlike the 10 years that it took the equatorial impact of the 1982 El Nino to propagate across the Pacific at 30 north, at the equator, within a month of the monsoon winds reversing direction and the waves crossing the equator, you want to see an impact on the current of Somalia. Because James Light realized that the response is faster near the equator, so rapid response to the ocean to changing monsoon winds. But this paper also did one thing. It threw out all possibilities of steady state ideas. Reflection at a distant boundary. The observations came in the 80s. These are from tide gauge data. These are tide gauges on the coast of the United States and Central America. And in the tide gauge, you can see that this is time and controls are still and you can see this is the north-south coordinate from south to north, and you can see that there is a propagation from south to north. But this was in the 1980s. Theory actually preceded it. Same picture that I showed you earlier from McGrady's 1976 paper. Herbert et al. Herbert was a student of Jim O'Brien in Florida State University. They published their papers together roughly in 1976. McGrady published with nonlinear solutions. Herbert, like other students of Jim O'Brien, was using a numerical reduced gravity model, 1.5 layer reduced gravity model. So in 1976, they predicted that you should see an impact of equatorial phenomenon, equatorial winds, in the tide gauge data of the coast of west coast of the US. And few years later, it was actually shown to be the case. There's a technology of ideas, the same thing. McCready and Jacob moved from basin to basin. 1970s, it was the Pacific. This was McCready's PhD thesis. Atlantic Ocean in the 80s, and Indian Ocean in the 1990s. The same chaps. The student kept changing in O'Brien's case. Very close link between not just observations and theory, but systematic observations and theory. You have a set of ideas that you examine. It is only then that observations you make are systematic. Otherwise, they're random. You just go out to see diversity, collect some data, and anybody can do it. But if you have some idea that you're testing, you're forced to design an experiment. You're forced to plan your observations carefully. That is when the observations become systematic. And it's only with systematic observations that you can match observation and theory. And progress depends on that. In the Indian Ocean, we had the International Ocean Inspection in the 1960s. Divecha, Minima paper, rapid response to Somali country, answer to summer monsoon. That's the title. Amazingly, the first major GCM simulation for any basin was for the Indian Ocean. 1970. Michael Cox, using the Brian Cox model, did an OGSM simulation of the Somali current. The first one was for the Indian Ocean. After that, there was a long gap. There was considerable work in the Indian Ocean. There was observation of the equatorial jet by Klaus Recke in 1973, and the theoretical explanation for that by Oakley and Humboldt in 1974. The basic theory had been laid in place by Yoshida in Japan earlier. The WICC jet is essentially a Yoshida jet. But once you move out to the forcing region, it's a Kelvin jet. The West India coastal current, it was Mansey in 1959. Tal Mansey is a biologist who spent quite some time in India in the 50s. He pointed to an undercurrent along the west coast of India. In 1968, G.S. Sharma and Tal Mansey, in separate papers, pointed out that a fairly is stronger in the south and that it moves from south to north. There is a fairly sensing first in the southern part of the west coast, and over time it moves to the north. They already observed that there is a flow against the wind. Mansey in 1959 had already pointed out that the prevailing winds are comparatively better. You have the ITC that's sitting roughly at the equator. You have northeasterly winds and the southeasterly winds on either side of the convergence zone, which is similar to what you see in other places. So the prevailing winds are comparatively better. But the western Somali current flows forward in the Arabian Sea during summer. The Somali current flows forward during the summer monsoon. During the winter monsoon, it flows equatorward. That's opposite in direction to what you see in the other basins. Shetty and Shah in 1988 noted that the western coastal current is comparable to other eastern boundary systems only during the summer monsoon. Because the classical eastern boundary current, like the Canary current, flows equatorward and you have coastal upwelling. So it was only during the summer monsoon when you have equatorial winds along the west coast of India that you have a classical eastern boundary kind of system. During the other season, you have a flow into the wind. There were many hydrographic observations, but systematic hydrographic observations in the Indian exposure economic zone made possible the theoretical treatment of the West India coastal current. He needed a set of time measurements, and this was done in a set of cruises that were carried out by Shankar and his colleagues from 1987 to 1994. The poleward West India coastal current during winter, they showed is driven by Alongshore salinity and therefore density and pressure gradient. You have lower salinity south in the south along the west coast because you have low salinity waters being dumped into the Bay of Bengal. The East Indian coastal current reverses to flow equatorward once the summer monsoon collapses, and the fresh water comes down to south of Sri Lanka. And that's the time the West Indian coastal current flows forward. It takes this low salinity water into the Eastern Arabian Sea. So you have low salinities in the south, you have higher salinities in the north. And that means you will have higher sea level in the south and lower sea level in the north. This condition is somewhat similar to what happens in the Nubian current on the west coast of Australia. So Shankar realized that this onward west India coastal current flows into the equator between because you have an alongshore salinity gradient and therefore an alongshore pressure gradient. Bruce et al. In 1994 identified what they call the magnetic pipe. It's an anglicized term, luxury pipe, in geosynchrometry. It was the predecessor of Topex Poseidon, and then in IIUV hydrography. So they first identified sea level high in satellite autometry, then they went back to the data from the 1960s. And lo and behold, you could actually see that feature in the data, in the hydrographic data. You had a data thermometer where you expected it. We showed in 97 that the luxury high and luxury low basically form an annual cycle of sea level of the west coast of India, of southwest India, and the annual cycle of sea level of west coast, southwest coast of India is related to the West India coastal current. You can't separate the two. They are part of the same document. You have eta and velocity. These are your two variables, u, v, and eta, determining the momentum balance and mass conservation. And the Rossby wave is basically the solution to that. If you go back to 1960s IIA data and look at the summer monsoon data, you can see features like the luxury low. But in the 1960s, if I were one of these authors, it would have required a leap of imagination to say that it is part of an annual cycle. The level of confidence in these data are not that high. You're not even sure if it's going to repeat every time. It's difficult to draw conclusions with some confidence. But if you go back and look at data from earlier hydrography, you can identify features that you now know must exist. So maybe hindsight is always cheap. It's easy to say that people who went before us didn't know as much as we did. But if you had the same limitation of data, would you have done any better? That's the more important question. A brief history of remote forcing. Potenga and Yu were also students of Jim O'Brien. In 1991, there were two papers showing that remote forcing from the equator, winds at the equator, affect the East India coastal current. Equatorial Caribbean reflects off the boundary of Sumatra, there's polar propagation of energy, and that Caribbean just goes around the perimeter of the bay. This is the benchmark paper, 1993, McCready. I have rarely been able to write any paper in which I don't cite this. I mean, if you don't cite this, to me it looks like they haven't studied the Indian Ocean. Comprehensive numerical simulation of the dynamics of the Indian Ocean confirms the importance of remote forcing on East India coastal current and suggests that remote forcing is important for the West India coastal current. This model didn't have salinity in it, but they still got the West India coastal current going into the wind during winter. Just like the dynamical model I told you of earlier, but that comes much after McCready's 93 paper, which implies that you don't need that alongshore salinity gradient. That explanation is okay, but you don't need salinity. Even without salinity, you can get the West India coastal current to go into the wind in winter. So we had some papers that showed the relative importance of the different forcing mechanisms of the IISc using a simple model. And Professor Divecha was unfortunately not here. He did his thesis at the same time with UGC, MOM. In those days, MOM was not what it is today. It was the Brian Cox model. It was like running one of those gold-style cars. If you didn't know how a car worked, you can drive. Today, you just turn on the ignition and you can just press the accelerator and move. It wasn't the case in those days. Then we were seeing the West India coastal current, McCready, and we showed we had an analysis of West India coastal current forcing mechanisms. Now, these two papers, McCready et al. 93 and our paper in 97, the Alongshore variability for the West India coastal current is actually set up by those coastal currents. Neither of these models has salinity, but it guesses the IISc flowing into the wind, propagating along the east and west coast of India, not by alongshore salinity gradient as the WICC paper. That may play a role, but it's only adding to the effect of the Caribbean. Or by an earlier explanation was the cross-shore salinity gradient. You have lot of rainfall in the summer monsoon, and you dump that ocean water off the west coast of India. Once you do that, sea level has to rise, and by Janshpati, you will get the coastal current that goes into the wind. That was the explanation by Shankar in 1987. The problem is that the lowest salinities are seen during winter. That's coming from the east coast of India. The reason I'm going through this history is because even today, you read papers that are being written now, you will find a lot of people quoting the Shankar 91 idea of the Alongshore salinity mapping to explain the forward WICC during winter. Not realizing that in 93, that we really could simulate it with a model that did not involve salinity, straight away implies that you don't need salinity to produce that effect. Even today, you will find papers being written. That's the reason for going through the history. The communication between the East India coastal current and the West India coastal current via the monsoon current system south of Sri Lanka makes the West coast of India different. It is not a typical eastern boundary because you have a boundary here that has a forcing coming from another boundary. It's not a typical eastern boundary. Canadian current is just the wind over there. There's nothing else. While here you have the east coast of India winds providing mechanism to generate Kelvin waves that go all the way around. So that makes the west coast of India different. The trouble with this idea was this remote forcing or the West India coastal current. Every time we wrote a paper, there was one question that would come. Where's the evidence for that? Observational evidence was very difficult to get because multimeter repeat cycles, though very good for the Rossby wave, are no good for the Kelvin wave. The Kelvin wave propagates at 2 meters per second, and a 7-day repeat cycle is not good enough. There are no data available that will give you the Kelvin wave. Until direct current measurements were made, there was no observational evidence for remote forcing the West India coastal current. So almost 2 decades after the idea was put forth, Shankar in 2008 and Nonlinear in 2012. First observational evidence for remote forcing of the West India coastal current. In the Pacific, the lag between our theory and observation was about 5 years. Here it was almost 2 decades. Because it's expensive to make these kind of measurements. That's the problem. Okay. Shankar used a very strange approach. These were data that were not collected for these kind of studies. They were collected for a coastal management program. 1 month long record of current meters of Goa. 5 current meters from Alongshore in the north. Alongshore is a beach in North Goa to Kolma in the south. A distance of about 70 kilometers. That's it. 5 current meters, of which we are looking at 1 wind. There was a wind measurement made on the terrace of Institute using an anemometer. So in blue you see the observed wind and in red you see the observed current. What has been done here is to take that 1 month record and split it into 2 parts. One is the high pass or high frequency part, that is periods less than 10 days because 10 days is the cutoff for the filter, and the other is periods greater than 10 days. If you correlate the high frequency wind and current with a lag, you can get a match. We got a pretty good correlation. So the idea was that high frequency or periods less than 10 days, that part of the current is driven by local winds. And look what happens when you look at the low frequency part. There's period less than 10 days, but roughly between 10 to 15. Because with a 30-day measurement, you cannot resolve any period greater than 15 days. So you're looking at a very narrow window, very small. This is not seasonal cycle. But you look at the wind doesn't change direction. Current is. The wind of Goa is in direction during this 1 month. But if you low pass filter the data with a 10-day low pass filter, the current reverses direction. If you look at mixed scattering data, which is all that we have to go as far south as Kollam in Kerala, that's roughly 8 to 9 north, to get a reversal in the wind. The winds do not reverse southward in Kollam and Kerala, a distance of over 600 kilometers. These current meters were not located on the continental slope because for the Kelvin, we are looking at the boundary as a straight wall. The coast is just a wall. So basically, we are talking about the Kelvin, we are talking about the current along the continental slope, not on the shell. These observations were made in the inner shell. The water column depth was 10 to 20 meters. And if you look at any of the environmental impact assessment studies, the typical measurement of currents is made at same depths. But if you look at any of these studies, and there's a model study or an explanation, the basin boundary will be very small. The basin domain is usually very small. The assumption being that so close to the coast, you don't have to bother about anything that happens far off. It's not true. Even at these shallow depths, so close to the coast, you have remote forcing. So remote forcing is important even in near coastal waters and depths as shallow as 10 to 20 meters. The way we do our environmental impact assessments has to change. I don't know when it will change. And whether it will change in my lifetime, I'm not sure. But it needs to change. That's the message. Okay, this is the last bit. To do some justice to what I've been asked to do. You have automated data now running for almost 2 decades. You take the data, you can filter them to get what you would call low frequencies, interannual periodicities. Now, if you were to take the altimeter data and at each grid point, you extract the response at a period of roughly 3 years and compute the variability. This is the kind of picture you get. There are regions where you have high variability, and there are regions where there is practically no variability. This is a logarithmic scale to base 2. So every number here, 2 to 3, implies a factor of 2 in the variability. It's coming from the wavelet transform. It's a wavelet transform, and then it has been averaged in time. It's easy to understand why you will see variability. You have these oscillating waves existing even at interannual periods. You have a sine wave oscillating at an interannual period, it will generate a oscillating wave at that period. So it's easy to see why there are regions where you have high variability. But why are there regions where nothing happens? Nothing seems to change. In this part of the Indian Ocean, along the southeast coast of India, almost throughout the west coast of India, the coast of Oman and the Gulf of India. Why does nothing happen? This is a simple model solution driven by insect winds, and you can see that it produces roughly the kind of features you see. Some details about, but you get this minimum variability here, you get this off the east coast of India, the west coast of India, in the Gulf of Aden, and along the coast of Oman. The question is, why does it happen? You take very simple winds, and basically there's no variability in zonal direction in these experiments, and you have a cosine function tapered off to 0 at 18 north and 18 south in the north-south direction. So it's maximum at the equator, and it's a cosine function that describes its variability away from the equator. There are two experiments here. One in which you don't have the strip showing India, and the other in which you have the strip showing India. When you don't have India, as you would expect, the solution is symmetrical or equator. The moment you throw India in, you get this low variability, which you see over here. The economic spreads along the west coast of India and along those boundaries. If you were to run it with realistic boundaries, I mean, you get basically what you see. The only picture here I want you to see is this one. This is sea level. But this is an analytical solution with no time difference. It's a steady state solution. You get this low variability here, you get low variability along the west coast of India and along this part of the Arabian Sea. As far as I know, there is no steady state solution after light wave that can explain everything else. When you see the Shankar paper of 1993, they have used the steady state spread theory. And the basic criticism that came was that we're talking of a time-dependent circulation and you're using steady-state Sweat analysis. And that's what started my research career. Just find time dependency into that solution. But here with the steady-state solution, you can explain why those minima exist, minima of variability. So if you take the sea level data and low pass filter with the running mean, at periods ranging from 18 months to something like 5 years, any period, you get this kind of structure. With some changes, you find a minimum of variability here along the southeast coast of India, but along the northeast coast of India, there's a lot of variability. Though variability along the west coast of India, along the coast of Pakistan and Iran and Oman and in the Gulf of India. In a linear system, these spots of variability that you see are seen more as a very smooth region of no variability. Because this is a linear model. What is happening here is that you have a nonlinear system, so there are pockets. But even the low frequency variability of a nonlinear system, if you just want to understand why it happens, the linear model is sufficient. The problem is that you see no variability out here. And it turns out that these are regions where the response, the sea level response of the Rossby wave is simply cancelled by the local medical response. So wherever in the basin, these two responses are opposite in sign, variability collapses. So if you look at the sea level record, there are regions in the North Indian Ocean and the Indian Ocean where you see no variability, which has implications, which means that the thermocline will remain roughly flat once you low pass filter the data. While in adjacent regions, like the coast of Sumatra, you see high variability. This is the region of IoT. You have IoTs out here, where nothing will happen. Thermocline is flat in time. Okay, sea level rise. This is a picture that shows you data from the west coast and the east coast here. This is a station of islands in the Bay of Bengal and the Arabian Sea. You can see one problem with the data. They are patchy. Aden is the only other station which has a record that goes back to the 1880s. But unfortunately, it ended in 1960s once the British left Yemen. When Yemen became independent, there was a collapse, the civil war and the tideways network broke down. So Mumbai is the only record that goes along there. And what you have here, this light lines, I'm not sure you can see any of that, is from Church et al., which is a model estimate of sea level rise for these stations. Now what you see is that the kind of line you would fit, which is done here, depends on the part of the data record that you're looking at. If you were to look at Mumbai, as I had done earlier in the 1980s, sea level had risen and then just dropped. It seems to have remained roughly flat and some minor increase in the 2000s. So it's not a very simple thing of sea level rising at so many millimeters per year all the time. The game is much more complicated than that. And very often you have records that are just this long. If you take the entire record for Karachi with all these breaks that are there, you can get a line that shows an increase. But if you throw up these measurements, you actually see a decrease. And this is intermittent analysis of data, especially for long times, because data records are a finite length, and the duration and the timing of the measurements may not be the same. So unless you understand those rigors that are imposed on the straight line, there's no way to explain what you see. It's easy to write 0.77 plus minus 0.08 at 99%. You don't need to know oceanography for that. All you need is the data and Excel. It'll do the job. That's it. It is in trying to explain why it is that number that oceanography comes in. So if you want to understand these phenomena, even in long time scales, particularly talking of sea level, you cannot ignore the tides. The first thing anybody has to do when given a sea level record, RV sea level record, is remove the tide. You want to do anything else, you have to remove the tide. You take altimeter data, you want to do anything with it, you have to remove the tide. And how is the tide removed from altimeter data? With a model, a numerical model of the tide. Then you have to make corrections. You have to make corrections for the dry atmosphere. You have to make corrections for something far else, the wet troposphere. Those signals that we were talking of are of the order of a few centimeters, maybe 25, 30 centimeters at most. The wet tropospheric correction is 1 meter. So from what is the raw record, you're actually removing a noise that is much larger than the signal that you're making. There's a huge amount of atmospheric science modeling. There's a huge amount of atmospheric science and tidal modeling that goes into giving you what is called data. When you see an altimeter record and you see all those wiggles and you see someone fitting a nice straight line, there's a huge amount of modeling that's going on. And then you have this gridding of the data, you have altimeter track, where there is 7 kilometer or 6 kilometer along track spacing of the data values, and across track spacing is the equator of 300 kilometers. Gridded into a very neat 1/3 by 1/3 degree grid, or quarter by quarter degree grid. They give you a secondary heavy fiber, like combining with other altimeters. They even give you daily products. You look carefully at those daily products. You can write papers with them. But you look carefully at them, there will be a step change after 7 days. Because that is the actual resolution of the data. So what you call data here are not like these tidal measurements, which is a simple movement of some stylus on paper, matching the water level. Even there is a lot of continuity that has to be accounted for. You must get rid of a base and do that in the mechanical system. There's a lot of theory that goes in, instrumentation theory that goes in. Let's ignore that. When you look at the data point, this is not like you take your temperature when you have fever. That's a very simple heat transfer. Two bodies have the same temperature, then there's no heat transfer between them. So you have to hold it for some time. Heat is transferred from your body to the thermometer, the temperature equalizes, and you read it. That's a different one kind of measurement. Or you have an anemometer weight taken away, you calibrate it. As long as the friction doesn't change much, you don't have to recalibrate it. You can use that. This is different. When you see an altimeter record, there's an incredible amount of modeling that's going on. Some of which is unbelievable. You're accounting for wet tropospheric levels, which means you know where the clouds are. You're accounting for all that, and that signal is not a meter. You're removing all that to get those 10, 20 centimeter changes. So when you say data, you have to be extremely careful. So if I have a model and I'm told to reproduce data, the trouble is that in most of what we call oceanography and atmospheric sciences, there's no such thing as data. The data has embedded in a huge modeling component, and unless you understand what that value means, it's practically impossible to do anything. And that's why research in climate is not about fitting a straight line. There's much more to it than that. That's the reason I went about this lectures the way I did. So there's much more to the sea level trend than fitting a straight line to the sea level data. You have those Minima sea level variability, you have the Indian Ocean dipole, you have El Nino, you have Madden oscillation, you have the seasonal cycle, you have tides, all kinds of things. So what's just my view? Years ahead for the North Indian Ocean. As far as observations are concerned, I don't think we'll make progress unless we have direct current measurements. We are doing that. Direct current measurements are expensive. Until about 2006, there were very short records made typically for sponsored, industry-sponsored projects. Maybe a week long, maybe a fortnight long. You put a current meter out in shallow waters, make a measurement, and take it off. Now we are making measurements using borings on which we have fitted acoustic Doppler current profilers. So you get a profile of the current for about 100, 200 meters or whatever, depending on the frequency of that instrument. But each mooring, even with just one ACD, costs about a crore. It's just the cost of the stuff on it, plus there's the cost of the ship. It costs about 5 to 10 lakhs per day to operate a ship. Doesn't matter whether you keep it at port or you are operating it out at sea. It's usually cheaper to keep it out at sea than to keep it at port. So oceanography is an expensive science, and these kind of direct measurements of currents is much more expensive. So it's only now, with the economy growing, that we have been able to do it. Earlier generations had no access to these kind of data. I told you about the remote forcing paper by Amol et al., published in 2012. It uses what's called coastal track wave theory. That was done in the United States for the west coast of the US back in the 1980s. My research guide, Satish Shetty, he wanted to do it in the 1990s for the west coast of India. There's no point. There were no data. I mean, he could have solved all those equations. But what was he going to do with the solution? I mean, he could write a paper, it probably will get published. You just have to keep sending it to a journal, somewhere it will get. But there was no purpose. 10 years later, he asked me to do it. Same problem, no data. It took another 10 years before there was enough money in the country to fund this kind of observations. So it's a chicken and egg story. You have a strong economy, you can do these kind of measurements, and these kind of measurements are useful only if you have a good economy, because then life becomes more expensive. Otherwise, people used to die when the cyclones would be bothered. The dead toll would be 1 lakh, 10 lakhs. It was just a number that was written on. Today, 10 people die, you can lose your constituency in the next election. Times have changed. So that is the key thing. That kind of measurements. It's no longer sensible to take a ship out just because you have to take a ship out. You have to plan carefully. Focus carefully, design hydrographic experiments to test hypothesis. And I will tell you to read just one paper, when I think it out 2013. The summer monsoon pump in the Bay of Bengal. It could not have been done without a ship and a CTD. Could not have been done. There's no measuring instrument today that can do it. Automated, mode, or whatever. Cannot be done without those fluids. It would not have given you the confidence that you had in the data. The kind of resolution that the CTD provides, the kind of confidence you can have in the CTD, you will never have in the vertical profile from Alpha. Models, the bigger the better. You need good computers. You need to, if you want to do that, simulate those currents seen of Arambol and Kolba, then you need a water column depth. You need to get close to the coast. What's the vertical resolution that you need? Maybe I will not be able to see it in my lifetime. Maybe you will. Those things will rely on resolution. Talking of high performance computing, there's one very critical bottleneck here. We're still teaching students sequential programming. You need to learn parallel programming from scratch. The learning curve after a PhD is very steep. One of my students recently parallelized the LCS code, linear continuously stratified model. Very simple parallelization. We were running it separately for each vertical mode, and this is completely independent. Each mode is totally independent. There's no coupling between them. But in order to justify being run on a parallel machine, I said we must at least parallelize it such that each mode is run simultaneously. To learn that API coding, there was no background with anybody in it. It took some time. It took him a few months to put it together. With help from outside mostly. Professor Ravi here and a colleague from CDAC. So this is something that has to be taught, rather than assuming that people will learn it on their own. You need data and wind forcing if you want to make forecasts. How good are our atmospheric models? You need a good atmospheric circulation model. You need data simulation. I'm not totally convinced that data simulation does well, and I have good reasons to believe that it can throw things off. But anyway, that's the way the world goes, so I won't dispute that here. Which means you need to initialize. You're never going to get enough oceanographic data to initialize well. Even today, the distance separating 8 Vigo floats is too large for good initialization. ARPO stands for Array for Real-Time Geostrophic Oceanography. The idea was that you could get geostrophic currents from it. That is not today. It's no longer an acronym. The original proposal was an acronym. Today it is just ARPO, it's a word. Because they realized that with this kind of spacing, those currents are moving. From a 2012 unit of NIISc of 2009, the paper published in Journal, Summer Monsoon Farm, we find some currents that I have difficult time believing. I'm not trained to accept geostrophic currents stronger than a meter per second. Even a meter per second is something that we check repeatedly. The currents are strong as 2.4 meters per second in the core of the sun monsoon current. Never seen these kind of and it's like a current stream flowing right through the Bay of Bengal. 2.4 meters per second. But it's correct because you check the calculation against the shaded or papers, you're able to reproduce what they published. So this is correct. All of us does make sense. You can't initialize easily, you don't have enough data. You need an adjoint model which is worse than the forward model. We don't have enough people who know how to get inside our model. Unless it's a taught to get a PhD. None of my students, for example, can get a PhD unless they can write a code. I don't care what kind of code, but if they can't code, they don't get a PhD. This has to be a serious job. It's not double clicking and these models today are plug and play. You plug in a USB stick, it does things. These models are like that. You double click and the model runs. Just change something in a file and bam, you have a climate model simulation. You don't need to know what is happening inside. But you can publish those papers. At the end of it, the solution is only as good as your abilities. Nothing better than that. When you give me a Formula 1 racing car, I won't be able to match Sebastian Vettel. I'll still drive it like I drive my Minima. That's for modeling. It has to be done carefully. But small is still beautiful. So you need high performance computing, you need high resolution models. Simple models will still have a role. And this is the reason you have to study geophysical fluid dynamics if you want to understand why that season curve behaves the way it does. I have no background in that statement effect. My only role in the paper was to get those labels out of the way. Otherwise, I wouldn't have been an author on that. What we actually need is a suite of models. You need the simple models, and you need those big models, the GCMs. There's a beautiful paper by Isaac Head in which he compares atmospheric science. You can ask Professor Srinivasan for it, he'll give it to you. Isaac Head, one of those respected atmospheric scientists, very different kind of chap. He compares atmospheric science and its growth with that of molecular biology. And he says here you have every guy running his own model, and they compare results. They don't match. You contrast that with molecular biology, where everybody studies the same organism, E. coli. If each of us had been studying a different species, molecular biology would still be where it was in the 1960s and 70s. The progress was made because there was consensus that this is the one they would study. Everybody studies that, so there are different angles from which you are looking at the same thing. That's not being done in atmospheric science. He doesn't argue against having many models, but he says you need a consensus on the suite of small models. You probably need a large number of GCMs, but the simpler models, which are practically gone today. In fact, Professor Srinivasan told me that MSc thesis I did is unpublishable today. And that's why it's never been published. I think it's a nice model, but he says it's just a toy. No journal will take it. I never published it in those days. Today it's probably unpublishable. But Isaac Head believes otherwise. And it says the tragedy of atmospheric science is that people are running just GCUs. Okay, thank you. So that's you have a lot of things here. You have dispersion curves, you need them, you need big computers, you need a ship, you need moorings, you need satellites, you need these floats, and without these, in a poor country like India, I would never have been able to do this. So I'm grateful for the free software that's available. Either that or I have to be a pilot, and I don't do that. Thank you. I have some animations, but if there are questions, I'll take them. We have 15 minutes, maybe we can continue a bit into lunch. Not sure of that. But if you want to see, for example, what those things look like, those waves. This is a nonlinear simulation. I show you the 6 panels. Lines here, and you can see these waves. Look at this patch moving westward, gradually across the basin. These are the kind of systems that exist. In geophysical fluid flows, from the word go, it's waves. You can do a 4-year engineering course, you can do an MTech, you will not have to study waves in fluid mechanics. Not that critical. But here it's a life or death issue. I have a linear system that I will dispense with. I'll just show you the East Coast winds. This is the effect of winds just along the east coast of India. From here to here. And you see the response. It has a huge impact on the circulation of the radiant side. This current will reflect direction. The wave always goes this way. The current associated with its flipping direction. Just keep that in mind. The Kelvin wave is mostly traveling northern hemisphere, most to the right. But if there is a sinusoidal cycle there, the current will keep changing direction. Okay, so we'll close this and this is that simple solution I talked of at the period of 360 days. Just how it functions. But when Shankar presented it in Washington, Dennis Moore told him it's not an analytic solution if you have to add so many modes. You can't do it without a computer. Just Crosby waves, upwelling, downwelling, just keep moving. This is the period of 60 days. 10 knots is the critical latitude. So you have coastal tracking forward of that as more predicts. And you have the roughly now shorter wavelengths moving offshore, south of 10 knots. If you move to 30 days, the critical latitude goes to about 3 knots and you don't have the westward propagation anymore. It's entirely coastal fluid. So at the lower limit of the MGM, if you have something in these coast winds, just shoot up along the west coast. Nothing will propagate offshore. These are things to be kept in mind. At 30-day period, you cannot generate a Rossby wave in the interior of the basin. You cannot do it. Unless you are practically near the equator. Okay, that's it. There were a few questions I said I would give at the end. So we can do that now. If you have any questions on what I spoke, you can do that. There were a couple of questions that I said we will take at the end of the lectures. Yeah.
You're talking about the remote forcing. So you were telling that there are some features in the current network that go up. We have to go out and be due to remote forcing that is happening in the southern ocean. So
Not South Indian Ocean.
Southern.
Southern part of the west coast of India.
Okay. Is there any extent of this limitation of the extent of this remote forcing? So that if we want to analyze, due to what reason these features are happening, we have to analyze a particular area. Is there a certain limit for the
Okay, the question is whether you know to what extent you have to go towards the source of these waves. Like the Kelvin wave propagates forward along the west coast. So how far south do you have to go from Goa to decide how big your basic boundary has to be? I don't have an answer because in the Amol et al. Paper, we found that even the southern tip of India is not enough. On the shelf, you can actually go back into the Gulf of Mannar because the shelf wave is trapped on the shelf and the shelf turns back this way. The trouble is that when you look at a coastal killing rate, you're looking at the seasonal cycle. It doesn't care for these small variables. And if you look at the Divecha altimetry paper, it actually shows you that. Or look at the Shankar hydrography papers. The East India coastal current and West India coastal current are trapped on the continental slope. There's a signature on the shelf, but the slope is where the current really exists, core of the current. Even in the Gulf Stream, it was not on the shelf that you see the core of the Gulf Stream, it's a little offshore. Now, when you look at the Kelvin wave, it doesn't see the Gulf of Mannar. It doesn't exist. So it just comes to the southern tip of India and it goes to Kanyakumari and then off. But the shelf doesn't do that. For the shelf, you have to go back into the Gulf of Mannar because the shelf doesn't exist from Gaur to Kanyakumari. To go into the Gulf of Mannar and come back. How far do you have to go? I don't know. At 10 meter water depth, I was stunned when I saw this. I couldn't believe it. I thought friction will kill these things. It doesn't. On the slope, I can believe that, but on the shelf at 10 meter water column depth, I wasn't expecting that result. But they go a long way. I mean, if you were to tell me later that you actually have to go to the coast of Sumatra to explain what happens at 10 meter water column depth of Goa, I would, right now, I would still say I'll be extremely surprised. But I don't know. If it goes that far back, I'm not sure we can ever be successful in forecasting those currents. The best models today don't reproduce the observations. They don't reproduce the observations even on the slope when you talk of interseasonal variability. That includes the ones done on Earth simulator. You can do that modeling, but the basic simulations are big problems. You can publish papers, you can make predictions, you can write big reports, but the basic models still have a fundamental problem. They don't get the monsoons right, they don't get the basic ocean circulation right, except the seasonal cycle. Even the best of them, highest resolution, 0.1 degree, ocean forecasting on the Earth simulator has problems. Compared with IISc data, they're trouble still. I mean, higher resolutions like they're doing it in COIS now, that is 1 by 32 of a degree and 1/48 of a degree, they did better. They're still problems. Sometimes they get that interseasonal band, sometimes they just don't get it. When you get it, why do you get it? When you don't get it, why don't you get it? No answers today. Because when you go to those frequencies, nonlinearity becomes important. The kind of experiments we have made here are no longer that easy to do. And when you're talking in terms of sea surface temperature, it's worse. Because heat transfer is inherently nonlinear. It's a direct return. Nothing can be done about it. Absolutely nothing. You cannot really measure it. It's an actual transfer from one point to the other through a physical movement of that water. It's u dt dx or u dt dz. That term in particular cannot be ignored. And there's nothing we can do to make it linearized. We do it in simple models, but there are big problems, the consequences.
Only OGCMs or development models which is coupled with the atmosphere. AOGCMs, do you run only OGCMs?
I have never done a GCM in my life. Any GCM. I don't know how to do it. In another 2006, we never had a computer on which we could run anything like a GCM. Around 2000, we got a computer we thought was good. When I came, we installed home and he told us you'll have to wait. In 2006, I think that was when we got a 16 CPU Vortex. We managed with some effort to run what it be Indian Ocean version of home. We borrowed it from IISc from the time. But it's only now that we have a cluster. This has 5 web cores. I don't have access to that, but maybe 256 cores. We can run a reasonable resolution model, but only ocean. There are atmospheric models and in models you can run. What is the purpose of running a model? You have a hammer. What do you want to do with that? Are you going to meditate or are you going to bang the nail into the wall? It can go both. What is the purpose? That determines what you use. And if it's a nail, you use a hammer. If it's a screw, you have to use a screwdriver. The tool has to be appropriate to the task on hand. Okay, the question is there any role of postal current in modifying the mixed layer depth? Yes. If I have a postal current, there is a failure or non-willing associated with it. Mixed layer depth changes. You can have it in two ways. You can either have the mass adjustment taking place, forcing a change in the current, which is typically true when you have the length scale greater than the Rossby radius, the local Rossby radius. That's the characteristic of length scale. C by F, where C is the speed of the gravity wave or Kelvin wave. So if your length scale of motion is greater than that, it would be mass adjustment, that is sea level first or pressure first, followed by the current. But if the scale is less than the Rossby radius, it goes the other way around. The current will determine the pressure. You can actually see those lines between the current field and the sea level field. Yeah. How do we distinguish Ekman depth and mixed layer depth? I don't think you see any Ekman depth in most of the Arabian Sea in the Bay, practically never, because the mixed layer is much shallower than the Ekman depth. So at the base of the mixed layer, stratification would be so strong, the density would change so much that you will have a strong shear at the base of the mixed layer. We do see currents that don't care about it. I mean, you find uniform currents, not uniform, you see a shear, the current doesn't seem to necessarily change direction. I thought you would have the surface current tracked to the mixed layer, but the ADCP data show otherwise. You can go right across. Pardon? Depth of no motion or mixed layer depth? Depth of no motion is different from mixed layer depth. The two are unrelated. Ekman depth is related to the depth at which the momentum transfer from the wind vanishes to a reasonably small amount, and that is given by the Ekman depth. But the level of no motion is something completely different. It is more ad hoc. For the Ekman depth, if I have the latitude, if I have the stratification, I can tell you what the Ekman depth is. But if you are solving a problem, you have to determine the level of no motion. In the Indian Ocean, 1000 meters seems to be pretty good for most purposes. Many of you are civil engineers, right? No? No civil engineers. Only two. So even you need to know about tides if you want to look at the waste disposal system of cities like Mumbai or Kolkata. Tides are important, can't ignore anywhere on the coast. Mumbai is nothing compared to what happens in the Gulf of Cumberland. Bhavnagar, the rating is 12 to 13 meters. It's a 4-story building. Over the tidal side, you sit on a boat, you go up and down on those stories. You try building a waste disposal system with that. How do you account for that variability? You have no choice, you have to wait for the tide to go out and then flush the whole thing out. So it's easy to say that you have problems with water level. Nothing you can do. You need a huge amount of energy to work against that gradient. But I don't think civil engineering is at all about tides.
So the currents there affects the base dissipative capacity of the area.
Pardon?
These currents affect the base dissipative capacity of the area.
They must be. Tidal currents are critical. But I have not seen any serious studies on this. You need measurements first. They're expensive, Most of these measurements are made for one particular industry. You want to set up a factory, you will sponsor a project because you won't get a license without that. You sponsor a project, somebody makes the measurements, some modeling study is done for that factory, and it's over. Tomorrow I go to the same place, same town, I set up another factory, I sponsor the project. Studies carried out only for that. But A1 plus A2, it's a nonlinear system. It's like you're standing out here, can't push your bed, you lean forward. I push you again the same amount, it's a stoppable. That's what these systems are like. There is no study in your carrying capacity. It's a politically sensitive thing too. It's a tricky balance between economics and biology. Yeah.
So, just a general view on global warming and sea level changes or sea level rise. Do we have any global warming and sea level rise? Like, do we have any quantified average say, like, we can't directly calculate this.
Well, the latest IPCC report, in connection between global warming and sea level rise, that's the question. The latest IPCC report says that it's the ocean that's been warming in the last several years when you seem to see the atmosphere having flattened out. Was it happening before? We don't know.
Yeah, that's about people were quoting like sea level rose by 50 meters, 20 meters in the past, like logical past or something.
It's risen by 200 meters.
Yeah, 150. You know.
I don't think there's a problem with that. No. I think those are pretty robust records. So where you're reading in Bombay High today, people might have been staying there 20,000 years ago. And Mumbai is just a few meters above sea level. Most of Bangladesh and Bengal is just a few meters above sea level. And the land is sinking out. So sea level rise is a tricky thing because it's relative to something. So unless your benchmarks are good and stable, you can't measure the rise of sea level by itself. So you need to benchmark the land movement carefully. But yes, the two are connected. I don't think any of the models today can simulate those changes. They're very big problems.
But you know that longitudinal level engineers are steady state. So that one has told any solutions that will be provided for configuration. So what kind of solution is getting discussed about?
The question is the solutions of Storm and Mark and Swedrope are not valid. That's what I said because the North Indian Ocean is not in a steady state. So what kind of solutions do you get in this Celsius continuously studied by now? It has time dependence. It's an absolute solution. It's not just rocket.
So what is its implication?
Pardon?
What is the difference between these two?
In one case, you have been in the steady state approximation. In the other case, you have not. In the context of the Laplace transform, in the case of Swedrope, Storm and Mark, you are looking at the pre-limit to infinity limit. In the other case, you are looking at the transients.
And that is not the same as quasi-steady state.
Not necessarily. It depends on how you define it. I have a bend that is changing direction. So where is the quasi-steadiness? You make an approximation based on some insight into a phenomenon. You don't drop terms without purpose. We do drop friction at times, but you have to be able to justify any assumption. And you must understand the limitations of any assumption that you make. The fanciest of models is approximate. So that you have a high-powered computer doesn't mean anything. You can go for a joyride in a Sukhoi or an F-16, but if you have to fly that thing, it's a different game altogether. And if you want to do climate science, it's a different game. If you're going to be making policy, it's a different thing. You still have to understand something, but not at the level of person who is working on climate science. And that distinction is what I see being violated very badly in this particular field. It's a very nice thing. Students come, they want to work on global warming. I say, find somebody else. I don't do that. I'm a mechanic. I go under the car and I'm looking at it. My face is greasy most of the time. If I don't like it, find somebody else. It's not my cup of tea. But without what I do, you can't do a thing. That's all I'm saying. And that's the reason for the talk being what it is. I'm an expertise in the curve, with a straight line. The isostatic, the glacial rebound, nice terms. And I understand that a bit, but that's about it. Okay, time for lunch. And so, just one thing I will listen to it. Recording stops, I think. I teach a course on geophysical fluid dynamics, and it's available.